We are moving on to another way to solve systems. You guys will have 3 matrices type ways to solve things by the time you're done with today's lesson and the next 2 lessons. Well, today is not another way to solve. Today's actually setting up. We used to do matrix algebra all in one day, and it's a really heavy lesson. So luckily today is actually not too bad. You guys will probably be like, oh yeah, this one's not bad. But it's because when we actually do that with inverses on lesson 25, it's tedious. And so I have decided to separate the homework into 2 days to feel less daunting. So today, hopefully, we'll feel like, oh, this isn't too bad. And then we have more row operations tomorrow, Thursday. Okay, so we've already kind of learned this. The following matrix is named, we're going to call it matrix A. We use capitals. We go row by column. And since it has 2 rows and 3 columns, we use a little subscript sometimes to label which part in there. Like this is A11. So like I would stand for your row, J would stand for your column index. So for instance, element A23 stands for row 2, column 3 spot. Don't worry that you're not really assessed on this. It's just helping us to understand how to do the algebra in a second. All right, there are 6 elements in a 2 by 3. And because this is a row, well, we'll get to that in 1 second, but because this is a row and a column, when we're doing like multiplication and whatnot, it matters the number. So we'll get back to that in 1 second. But this matrix has 6 different elements. All right, and it's called the order. What's the order of this matrix? So what's this order of this matrix? It's a what by what? 1 by 1. Good. What's the order of this matrix? 3 by 1. And then I don't know why this one has a gap. There isn't a row that's missing. So based on pretending there's not a gap there, what's this one? 2 by 4. Good. So hopefully you get pretty used to recognizing the order. 2 matrices are equal, said to be equal if they have the exact same order with exact same corresponding elements. There's a row 1, column 1. So that one's a row 1, column 1. There's a row 2, column 2. You can't have one, like they wouldn't be considered equal if one had like an extra element. They have to be the same size. So since these are the same order, I could solve for missing parts. So if I claim that this is equal, like if I claim that this is true, hey, this matrix equals this matrix, what would you guys be able to say? Yep, you'd be able to say x equals 5, and what else would you be able to say? Y minus 1 does equal 6, therefore y would be a 7. Yep. So knowing that, if they ever gave you, so this is just basic algebra and arithmetic of matrices. That's why it's called matrix algebra. Is we're learning what algebraic steps you guys are allowed to do with matrices and what operations you do. Because there's some things that are not allowed. Sorry, I had a note on here, and I wondered if I can save that for another time. I'm trying to decide if I need to teach that part too. No, I don't need to teach that to you till Kramer's rule. Okay. I will be circling back to this little index thing when we learn lesson 26. So it was a note I was leaving for myself. Okay. Here are some things you are allowed to do with matrices. One is scalar multiplication. Scalar is a number only. Okay. You can multiply a matrix by a number, known as a scalar, by multiplying each individual element with that number, okay? So the process is called scalar multiplication. So if I tell you, and I gave you a matrix somewhere, and I tell you to do 5 times A, it's technically telling you to do 5 times all those elements, and that means you get a 5 here, a 10 here, a 15 here, and a 20 here. So this is matrix, or scalar multiplication. And again, if we simply say 5a, or if I just simply say -3 times that matrix, again, forget about all these little extra bars. These extra bars didn't transfer well. All right, give me the elements. What would we get? -12, 3, 0, -12. Good. This is super intuitive, super straightforward. Because there is a part that's not super straightforward, but this one is. All right, are you guys okay with scalar? Okay, next thing. You are not allowed, you can do, sorry, I thought we were moving on to a harder thing. You can do adding and subtracting pretty seamlessly. It is allowed as long as the order is the same. So you could do A plus B as long as the order is the same. Again, sorry about my formatting. Gosh, these are supposed to look prettier and look a lot more alike, but like this is supposed to look like a nice, pretty, just 2x2 matrix. Nice, pretty. I mean 2x3. Nice, pretty 2x3 matrix, and then this one's a 2x2. It just was taking me too long to edit those. That didn't turn out very well. So A plus B works, right? With adding and subtracting, you literally just get to add the exact corresponding elements. As long as they correspond, then you guys are allowed to just straight up add and subtract those elements. You're also allowed to do something like this, like B minus 2 times A. You just need to make sure you times the 2 through it first. You can do stuff like that. So let's go ahead and do A plus B first, and then we'll talk about a C plus A really fast. What would you guys get for A plus B? Very good, even with my mess. I'm not looking. What about C plus A? Is that allowed? No, they don't have corresponding elements, so you can't do it. And then we could do subtraction, okay? On 2 times A, you would make sure you just distribute that first. So on this one, I would probably rewrite my B as my 4, -2, 3, 0, 1, 2, and then I would probably put a plus sign and have distributed my -2 through. So I probably would have made this a 4, -2, 0, -6, +2, and -10. So I probably would have distributed that -2 with, I probably wouldn't have done subtraction. In fact, even on this minus, to be honest, I probably would have taken this first, just for the math, turn it into a plus, and then I probably would have multiplied a negative through all my B elements. Just that way, it's just so much easier to add, and you don't mess up on the negatives as much. So I would have distributed the negative through. Okay. All right, so pretty straightforward. I feel like this original, this first thing that you guys are learning, super intuitive, super straightforward. You do exactly what you think you should do, and you guys should be good on that. It's matrix multiplication that will maybe challenge it, just a tip. Okay? Have I lost anybody with matrix, all of this so far? Everybody okay with this? Okay. So the last thing that we're asking you to do today is matrix multiplication. This one is it takes a little more thought. Matrix multiplication is very finicky. You've got to be really careful and organized. It is not as intuitive as you think. You don't get to just do element 1 with element 1, element 2 with element 2. It's just different, okay? And in fact, you don't do it that way at all. So make some note to yourself that it's different. You have to make sure on this that the number of columns of matrix A, which is this is your number of columns, has to match the number of rows with matrix B for these to work out. So I essentially see if I can do it by seeing if my column and rows work out. And if they're the same, my matrix A times B will result in an M by P. Okay, so if my columns lines up with my rows, it'll work, and you'll see why. Because you multiply your column with your row for that element. Okay, so matrix multiplication is not commutative. It is not commutative. A times B is not the same as B times A. You can perform multiplication A times B by multiplying one entire row of matrix A by one entire solid column with B. Okay, so we'll talk about it and I'll show it right here. And then this is the last of the lesson anyway. Okay, so let's do C times A and then A times C, and I'm going to show you how they're different. So first off, you want to make sure it's allowed. C is a 2 by 2. A is a 2 by 3. Do you guys see it? How it's a 2 by 3? Since they are the same, I'm allowed to do it. And what's the resulting matrix going to give me? A 2 by what? It'll be a 2 by 3. So this is the way I organize myself. I put my first one first, because you're supposed to. It matters because it's not commutative. So I will always put C first. Now, the way I organize myself, I would put a times and write my matrix next, but I actually lift it up just a little bit, because watch. I'm going to write -2, 1, and 0, 3, -1, and 5. And I want you to watch this. When I extend this down and divide them, what do you guys notice? How many elements do I have in my result there? Do you guys notice how I have the 2 by 3 there? I have a spot for my elements. So notice how I have a spot there, right? Okay? That's going to give me a 2 by 3 when I'm done. And this is how it works. You move across this one's row, because that's why it matters how many columns you had, with this one's down this one's column. So across this one's row with this one's column. And that's how you times and then add those. So watch how this works. 2 times -2 is a -4. And then I'm going to add that with, jump to the next spot, -2 times 3, which is -6. So my resulting matrix in row 1, column 1. So row 1, column 1 spot. This is my row 1, column 1 spot. That means I multiply the row 1 vector with the column 1 vector. So again, this is my row 1, column 1. This is my row 1, column 2. This is my row 1, column 3. This is my row 2, column 1. This is my row 2, column 2. And this is my row 2, column 3. Those are the vectors you times by as you guys are getting those spots. So I would have this be a -10. Okay, let's do it again. What gets to be added with what for my row 1, column 2 spot? So I go row 1, column 2 to get to that spot. It's going to be -2 plus +2. Who saw that? So it's a row 1 with your column 2 vectors to get you the row 1, column 2 spot. Oh, where at? Oh, sorry. Oh my gosh, I'm sorry. Oh, I erased the wrong thing. Right here. I must have been looking at something different. So we have a 4. Okay? Thanks, you guys. All right, let's do this. Row 1, column 1. Row 1, column 1. We have a. Do you guys see that it's a 0 plus -10? Okay, let's do row 2, column 1. What do you guys get? -6 plus 9. Good. Let's go to my row 2, column 2. Do you guys get 3 plus -3? What do you guys get for row 2, column 3 spot? 0 plus 15. And that's our resulting matrix. So to me, organization is key. The second matrix, I always raise it up, and then I mark my rows and my columns, so I know what my result will be. Now, it's not commutative, because if I try to do A was a 2 by 3, right? C is a 2 by 2. Does it work to do A times C? It won't, because your column and rows won't work out. So this one is not allowed to do it. We can't. It's not commutative. You'll get completely different matrices. What's that? Do you want to try another, or do you want me to go through the true false really fast? Okay, let's jump to the true false, and if you guys feel like you know it, great. Maybe I'll use this as maybe a warm-up in case. Okay, if A and B are square matrices, so 2 by 2s or 3 by 3s or whatever, in the same size, can I do AB and that's equal to BA? We just learned it's what? Not commutative. So timesing does not work. So this is false. Unless for some reason, unless there's an identity matrix. So if one of those is an identity, then that's different, which we'll learn next time. Okay? Because it's like me timesing by a 1.
What makes it an identity?
When the matrix was like 1s and 0s. So it's pretty much like timesing by a 1. That's an identity matrix. If A and B are square matrices, meaning they just have equal, like 2 by 2s, 3 by 3s, then can I do A minus B? Yeah, we can minus them. And they're both square equal size. You are allowed to do A minus B times by A minus B. Things are commutative. Are not commutative, but if I do A times A, it's A squared. AB and negative AB would give me 2 of those, and then B squared. So this is actually a true statement. Because I am allowed to, I'm not changing, I'm not making things commutative, trying to act like it's commutative. So this is a true statement. If A and B are square matrices of the same size, then I can also do that as well. These are both just true statements. Okay? What I can't do is BA though. I can't switch that order. Okay? Do you guys want to do, Nora?
So I was just saying, so if it's a square matrices, so it's 2 by 2 and the other one's 2 by 2, why can't you?
Because it's not commutative.
So how do you know which one is right then?
You just can't do A, B, and BA. So kind of like what we did up here. I see what your question is.
Yeah.
Well, it's still not commutative. So is it necessarily the same thing? Like, I can add things that are the same size, but I want you guys, mathematically, if we were to try it, let's go up here where we have some space. Let's do one that's easy. Are there 2 by 2s? CD, DC. I'm going to let you guys just work, and people go to Flex. I'll look up the teachers. Let's hurry and do DC because of the practice, and then we're going to do CD and notice that they're not the same. Okay, so just because they're square matrices, it doesn't necessarily mean, yes, they're commutative. They are never commutative unless it's an identity. Okay, so just square matrices is going to throw you guys off because you think, oh, it's a 2 by 2 and a 2 by 2. Sure. These did not only just not work because of their size. So I need to kind of clarify that as far as the word commutative. It's not just because of the size. Here we go. So let's do DC and CD together. And you guys are welcome to tune me out if you don't need this. And it's now just a work period. But let's go ahead and do it for those who want to have extra practice. So I'm going to do, that is actually kind of a typo, but I didn't realize that was part of that one. Let's do one though. Let's do one that is a square matrix with a square matrix and show that they don't turn out the same.
Wait, is it different because it's like 1 to 3 by 2 instead of 2 by 3?
Say that one more time.
Is D different because it's like a
No,
3 by 2?
my formatting spread it out too much. It's a 3 by 2. Yeah. Let's try and do an example though. I'm gonna use like C for a second. We're gonna do a matrix where I'm gonna times this one, 2, -2, -3, and 3. I'm gonna just do easy numbers, okay, you guys? Just to answer that question that, that Nora and I were just talking about. Okay, let's go ahead and do a 2 by 2 by a 2 by 2. Just because they're square matrices doesn't necessarily mean they're commutative. So let's just practice our timesing just for the heck of it. What two numbers will be added for row 1, column 1 spot? 2 plus -4. Are you guys kind of wrapping your head around that? So I move along. 2 plus -4. Move along the row vector with the column vector. Okay. What about this spot? Row 1 with column 2 spot. Close. Row 1 spot with the column 1 is 0. So row 1 and column 2, 0, and do you guys see that it's -8?
Yeah.
Okay, good. Let's now do row 2, column 1. What do you guys get? Yep, -3 plus 6. You're seeing it. Okay, let's do row 2 and column 2. What do you guys get? 0 plus 12. Good. So let's look at what that gives us for our matrix. Do you guys get a -2, a -8? Do you guys get a 3 and a 12? Okay, let's reverse those and show if they're commutative. So we're going to redo this. Oops, I need some space above me. This is just kind of a side example. I'm going to reverse this and do 1, 0, 2, and 4. The only reason this would work, by the way, we're going to talk about this, is if they're inverses. And so normally they're the same day, so we get to talk about it, but we separated them. So notice how I moved that to be the second matrix, okay? So I switched the matrices 1, 0, 2, 4, and then 2, -2, -3, and 3. Everybody with me? Let's do this matrix multiplication now. Okay. Do you guys get 2 plus what? 0. So already I don't even have the right element there, right? Let's try this one. 1 times -2 is -2 plus 0. Let's do 2 times 2, which is 4. 4 times -3, which is -12. So that's a -8. And then I get 2 and -2, which is -4. 4 and 3, which is 12. Positive 8. They are completely different. So just because they're square matrices doesn't necessarily mean they are equal. Okay? They throw you off by saying the word square. But we will talk about identities and how that can change a few things, but that will be next time. If you guys want to practice D and C and B and D and want to ask for the answer next time, feel free to do those out and make sure you have them. This was supposed to look like a 3 by 2 matrix, and it put a little gap between those, and I don't know why. Because of the formatting. So that matrix D is that. So if you want to check yourself, go ahead. I'll answer your questions next time.